Next talk will be done by Mikhail Belogolovskii from Kyiv Academic University. The title is Novel Superconducting Devices for Quantum Sensors and Metrology. Please, Mikhail.
Thank you very much for the invitation, and it's a pleasure to present the results obtained by our team. Our team is very informal, so officially it doesn't exist, and it is based only on a voluntary base, and it consists of internal refugees of the first wave. So we left Donetsk in the 14th year, and now appeared in different places. And also we have some colleagues from Kyiv. So it is a list of the main researchers, and I am some like a coordinator of this team. What I want to do, I want to present very briefly some results, some important results obtained together by these people. And my main task is to advertise them and to propose collaboration, to ask for possible collaboration, partnership from Ukraine and from above Ukraine to reveal some problems that appear. The team consists mainly of theorists, so for us it's a very important collaboration with other experimental groups. So I divided our activities into 4 domains, and we'll present some results together with names of people who did it. And so the first part is about the fundamental study of proximity effects in superconductor-based materials. Next is about contact spectroscopies of superconductors, so that is point contact and tunneling spectroscopy. After that is about more practical issues about novel Josephson junctions, just for quantum sensing and metrology. And the last part is about educational activity at the Donetsk University that was relocated to Vinnytsia. So the first part about the proximity effect, I start with re-entrant superconductivity. It is not the experimental figure, but something similar can be observed experimentally. So you are going from above, from higher temperatures, suddenly at critical temperature, the superconductivity appears. After that, it disappears, and at lower temperatures appears again and disappears. So there are such 2 regions where the superconductivity exists. Usually, it was observed in samples with magnetic impurities and was related to magnetic ordering in the studied samples. But Eduard Zubov showed for the first time that theoretically that such a phenomenon can be observed in hybrid normal metal superconductor and ferromagnetic superconductor structures. So it has not been checked experimentally. In fact, so it would be very interesting to verify theoretical predictions in experiment. The second issue within this domain of activities is unexpected quantum properties of nanocomposites, which is formed by a superconductor. The superconductors were with comparatively high critical temperatures and a half metal. So it was a manganite where with nearly 100 degree of spin polarization. What was unusual is a great difference, a huge difference in the sizes of superconducting grains and half metal grains. So difference was at least 2 or even 3 orders of magnitude. So the size, the diameter of superconducting grains was about 5-10 microns, and the size of the manganite grains was about 10-15 nanometers. So it was, you can imagine that it's something like a great ball, a superconducting ball that around it there is a shell of strongly ferromagnetic material. What was observed that the superconducting transition starts from the critical temperature of magnesium diboride. As a superconductor was used magnesium diboride with a critical temperature about near 40 Ks. And after that, there is a broad transition, and the shape of this transition was explained by Berezinski Kosterlitz-Sauerles transition effect. So, so it was most probably the first observation of such KBT transition in a three-dimensional sample. And it was explained that this transition is at the shell around the superconducting grain. Even more exotic were the results of point contact spectroscopy on such nano composite, where two superconducting gaps character for magnesium diboride were revealed. So it is naturally, but also there was a third gap above them, so higher than them. And this third gap was observed very regularly and in a repeatedly way. So there are no doubts that something similar like a third gap exists in just only in this nano composite. The explanation of the authors is that it is a gap that is induced in magnetic manganite by proximity with a strong superconductor like magnesium diboride. In other experiments, it was a bismuth-based cuprate. In principle, this looks very strange, that it is something similar to the well-known story of Münchhausen, who succeeded to take himself by hairs from a swamp. So how it can be that a smaller energy gap introduces in a magnetic material, in a totally spin polarized material, larger gap. So the explanation of the authors is such that really, not explanation, hypothesis, I would say, is that really in the manganite, there is already local superconductivity, but there is no global superconductivity. And this superconductivity should be, of course, of the spin triplet origins, otherwise it cannot be in such material. But the proximity to magnesium diboride in these samples, it helps to the manganite to create a global superconducting ordering. So it should be checked more, I would say, and of course, new experiments should be done with these materials that can be provided by my colleagues. And the last one from this domain is about magnetic pinning in the context of in the multi-layers with superconducting and weak ferromagnetic films. You know that the transport properties of second type superconductors are strongly degraded due to the presence, usually are strongly degraded due to the presence of abrikosa vortices. So how it is done? Often it is done by introducing pinion centers that immobilize the vortices, so the critical current is increasing. In our case, it was realized, in fact, it was experimentally realized in Bratislava. So such a three-layer system where we had a superconducting film and a weak ferromagnetic film, which were divided by ultra-thin aluminum nitride, so by an insulator. And in this case, the critical current density was strongly increased, while the critical temperature remained the same. So our explanation is that here there is an interaction between magnetic field of the vortex and the magnetic texture of the weak ferromagnetic this layer. And this results could be and should be continued further with new materials, new combinations, and so on. The second part is about the spectroscopy experiments. I already told about magnesium diboride, and magnesium diboride is known to be a benchmark two-band superconductor with two different gaps. And why can we observe two distinct gaps? Since there is almost no interaction between the two bands in this material. But if such an interaction exists, not strong, of course, otherwise there will be a single gap, but some moderate. And in this case, we could observe some new issues which are not present in single band superconductors. So it is important to find new two band superconductors and to perform experiments. So we proposed molybdenum uranium alloy as such a new two band superconductor. We performed tunneling and point contact spectroscopy measurements, and the results are shown here. This part reveals, in our opinion, two gaps which at sufficiently great distance. And here there was observed periodic structure, and this periodic structure was assigned to so-called Leggett mode. Leggett mode was proposed in 60s by Leggett, and the idea is that if you have interaction between two bands in superconductor, between two gaps in the superconductor, in this case there will be some oscillation relative to the difference in phases of the two groups of superconducting condensate. The next thing relating the contact spectroscopy is our attempt to create together again with Slovak colleagues from the Bratislava University an idea to try to fabricate such a device where you can switch between tunneling and point contact regimes of spectroscopies. It's known that point contact to observe energy gap and phonon structure in a tunneling regime, you need a barrier between injector, a counter electrode, usually normal, and a superconductor studied. And in a point contact experiment, you need a direct contact between the tip and the superconductor. So it would be useful and interactive to try to create such a system where you are able to switch between two regimes. The idea was to use the insulating layer between the studied superconductor and that was in this case magnesium diboride and the counter electrode that was platinum, and to create it with titanium dioxide, which is known as a material that is switching between high and low resistances or after applying a voltage bias, voltage pulse. So it is known as electroresistive effect. So it was done and such structure was created, and results optimistic, but we need to continue this study that is able to switch between the two regimes and to perform measurements with the same sample in the two regimes, and after that to compare the results between them. And the last one, again with Slovak colleagues, was the explanation some unusual features that often observed in superconducting point contacts, in particular some above gap conductance spectrum. Now I want to try to transfer to maybe more interesting, since it has direct practical applications, about new Josephson junctions that were created by us with, after that I'll say, the group, the experimental group which participated this experiment. The first part is poorly done in Kyiv. You know that the main part of the classical superconducting electronics, classical in the sense, of course, superconductivity is a quantum phenomenon, but classical in the sense that all is built based on the classical approach. And so in such experiment, in such devices, the main part is niobium electrodes. So as it is written in the recent overview, niobium is a workhorse of superconducting electronics existing now. So it is well developed, but it's too complicated process. And the colleagues from Kyiv Academic University, they proposed a new approach for forming the conventional niobium-based heterostructures. What I want to tell is about the results obtained with American colleagues. It is a new type of Josephson junction where the barrier, the weak link between two superconducting electrodes, again made of niobium, is a multi-layer of nanometers thick, 1, 2, 3 nanometers thick aluminum and nickel. So you can see that it's a complicated structure, and even in the center of the structure there is aluminum oxide, so a dielectric. And besides the aluminum oxide, there are also 10 bilayers of such a periodic structure. So in spite of this complicated weak link that with the width of more than 50 nanometers, the Josephson junction was observed, but it is not the main strange thing. What usually is observed in the Josephson junction when you apply a magnetic field. I want to show the next slide. And here you can see the so-called Fraunhofer pattern. It's the dependence of the critical current on the magnetic field. This shape of this dependence is well known and written in all textbooks, and everywhere it is written that to verify if you are dealing with a Josephson current, or maybe with a direct current, supercurrent across a pinhole, you should measure the critical current versus magnetic field dependence. If you obtain the Fraunhofer pattern, in this case, it is just a Josephson junction. But in several tens of these junctions, with aluminum oxide and without aluminum oxide, there was not observed a Fraunhofer pattern. But such a periodic structure, which is typical for squids. So we name it squid-like oscillations. Thus, for the first time in a Josephson junction made of simple metals, we could obtain such a periodic structure as the dependence of the critical current on the magnetic field. Sometimes it was such a strange curve with some beats. What does it mean and how to understand what happens if you replace a trivial aluminum oxide or maybe trivial aluminum or aluminum, nickel aluminum weak link with such a multi-layer? It is difficult to answer this question. In our paper that was published in Physics Applied, there was proposed a quantum explanation. So imagine that you compare the situation in the central part of this device and near the edges. In the central part, you have a shortest way from one electrode to another. But the structure, of course, is strongly disordered. Since the thickness of the layers 1, 2 nanometer means that it is not a good film, but rather it is a conglomerate of different grains. Therefore, we have a strong scattering, and if we are speaking about the central part of the junction, in this case, we have some trajectories to the left of this part and trajectories to the right part. They can cancel each other. And the result in the center, there is no supercurrent, or it is of a very low value. Another situation is near the edge. Since near the edge, you have only trajectories from the right side here and from the left side. So there is no such compensation as in the center. And the most strong situation is near the hinge, so near when the current is one-dimensional, like. And so,
sorry, Mikhail, it's
yes.
time.
Okay, I'll
2
finish.
minutes.
Yes, I will go. So I have two slides. We need more explanation. Maybe it is not for quantum situation, but something like a non-Hermitian system with edge currents. The last thing what I wanted to tell is about Josephson junction based on amorphous molybdenum germanium superconductors. So it is the first Josephson junction based on amorphous superconducting films in the literature. And the results were excellent, were very trivial and very excellent. So it can be that in future we can transfer from niobium layers to amorphous superconducting films. The Josephson junction should base on them. And the last issue I wanted to say about our plans that have not been realized due to the war. So the Donetsk University in Vinnytsia, they got an idea to start to train STEM teachers. STEM is acronym for the science, technology, engineering, and mathematics. So such to combine different subjects in in the same program, and we planned a quantum physics curriculum. There were planned for modules, and this September there was such a plan to start such this first students for this, but to teach STEM teachers, and but unfortunately, the war, due to the war, all stopped. So it is the end of my talk, and I'm thankful for your attention.
Thank you for the talk. Very interesting, very nice. And this talk shows that quantum physics in Ukraine is in many centers, not only in the Kyiv, Kharkiv. And so, do you have questions? There is question from the chat from Oleg Turutanov. Do you expect the quality of those Josephson junctions with the multi-layer barrier become better with increasing number of the interlayers?
No, I think that the quality will not increase, but it will help to realize a transition from squids, from nano squids, which are very difficult to realize at the nanometer scale, to single Josephson junctions. And these single Josephson junctions can be used for already for measuring ultra low magnetic fields. So it was not our task, and I think that we need a lot of work to get good quality such multi-layer Josephson junctions. Another situation is with junctions, Josephson junction based on amorphous fields. In this case, their property is already in the first experiments. We observed that the quality is better than the quality of niobium-based junctions. So, but I need more time to explain what kind of quality and why it is better than niobium. Yes, so it was the task of this second type of Josephson junctions, and it has been realized also in this case. Also, we need more and more work in this direction.
Okay, so if there is no more questions, so thanks again for the nice talk.